So our next speaker is Eric Ma, who's going to be telling us about agentic coding. So rather than doing the questions at the end, Eric's told me that we're going to spend a lot of time waiting for the LLM. So they'll answer questions in between. And so I'm gonna walk around with microphones, and whenever there's a gap, we'll answer some questions.
Alrighty. Hey everybody, my name is Eric. I work at Moderna. I'm one of the data scientists there. The topic today is how to do agentic data science. And I had a choice, right? I could tell you how to do it, or I could show. So I decided I'll show. Also, I hate making slides, and I hate sending them through the approval process at the company. So here's what we got, all right? So how many of you use coding agents? Everybody, amazing. How many of you use Marimo notebooks? No, only a few, great, okay, cool. So Marimo notebooks are gonna be the front and center piece here because I believe Marimo notebooks are showing us what a taste of the future of agentic coding for data science looks like. It may not be the tech of the future, but it's definitely showing a lot of cool stuff. It's a canvas, you get a pair code with a coding agent inside a Marimo notebook. And to show this, I'm actually gonna do a live analysis of some data that I worked with from my days at Novartis. Or actually, I have two adventures. I'm gonna take a poll, so we can go either way. Let's raise the stakes even further, all right? I could do, in front of you, a live analysis of microRNA data or protein meltome data. Who wants to do microRNA analysis? Okay, who wants to do protein melting points? I think protein melting points just won by a hair. And I prepped entirely on the microRNA data set. So let's go. To launch Marimo, you actually can run Marimo without ever installing Marimo on your system. You use UV. How many of you know UV? It's a Python package manager. Great. This is a crowd that is much more knowledgeable than many other crowds that I have been at. UV is a great thing for package management. It also comes with UVX, which lets you install run tools like NPX does for the JavaScript ecosystem. This does it for the Python ecosystem. I'm in Cursor. I'm going to be using Cursor's built-in browser and whatever. You don't have to use Cursor. Cursor's not sponsoring this event, so Ilya, if you get the recording, get them to sponsor this event because it's a great event, and there's a chance for agentic stuff with data in the loop here. Okay, so Marimo notebooks look like this. They're kind of an iteration on Jupyter notebooks, but they come with some advantages, which I'm not going to tell you up front. I'm going to let you observe them real-time live, and so you can see how things are going. So what I'm going to do is we're going to do the protein meltome data set, okay? And I'm going to talk with my data. Hey, I want you to connect to my Marimo notebook running on port 2720. It is live-demo.py, and I want you, once you've connected, to load in the data sets from the data directory inside my folder. It is the meltome Parquet file that exists over there. Please make that happen. Do it inside the Marimo notebook using Marimo code mode. While the agent does its stuff, I'm just going to give you a quick orientation around here. All right, I have live-demo.py. Ignore the fact that I have two demo notebooks. One of them is actually kind of empty. There's the Drosha data, which we've said we're not going to do. That's the microRNA data set. Then there's the protein meltome data set, which is basically a characterization of protein melting points across multiple domains of life. And what I want to do today with the protein meltome data set is actually double check whether we can redo this analysis and do it in a way that actually is fully Bayesian. Because if you know I am a Bayesian, I think Bayesian statistics is the only logical way of doing statistics. Hot takes. All right, spicy takes. It is the only way that allows you to go in and make statements about probability in non-convoluted ways. All right, that's not a hot take. So what we're going to do is we're going to try to create a Bayesian hierarchical model of protein melting points within the 22 minutes that I have left. All right, within the Marimo notebook. But at the same time, we're also going to do some quick sanity checks, right? Like the things that a data scientist is supposed to do, the things that we're not supposed to skip right past and go into our modeling efforts, right? And so that's one of the things that we're going to be showing live. You may have seen just now that this notebook actually does not live so first off, this notebook does not live within a heavyweight Conda environment. How many of you angled Conda environments and suffered? Keep your hands up. Yeah, so have I. It's painful. Notebooks can sometimes need and demand transient dependencies that you don't really want to put in your Conda environment, but you just need for the time being. Well, it turns out Marimo notebooks, because they're all just .py files, they respect they respect PEP723, which is Python's standard for inline script metadata that allows a Python script to specify its own dependencies, which means this notebook is, as long as I write it a certain way, which is to say don't hardcode paths on to my local folder, as long as I write it a certain way, this notebook is fully portable from my machine to yours. You will have the entire environment recreated for you live on the fly when you launch this notebook. All right? So that's one of the advantages. All right, cool. So we got the meltome curves data frame over here. We've got some columns, which I'm aware of. I've used this data frame data set before. There's the fold change column, which we'll see is the thing that is the signal dynamic range. It goes from high to low as temperature increases. We have a few other things, a few other data points inside here. So what we're going to do next is we're going to actually go and plot the, I'm actually realizing this data frame is kind of missing the temperatures at which the fold changes were measured. Okay, yeah, because I prepped this data frame this morning from the JSON file. So we're actually going to need to tell the coding agent that. As I'm observing the data frame, the Parquet file that you read in, I'm noticing we're missing the temperature column at which the fold change was actually measured. So there's a JSON file that has the full dynamic range of data that's inside there. And that's just for everyone's edification. That's this file over here, full dataset.json. I want you to see if the temperatures are inside there. And if they're not, I want you to go look online for the original paper from which the meltome dataset was produced and grab me from the methods section the temperatures at which these measurements were taken. Okay, so while the coding agent works, I'm going to open up for the first round of questions. Do people have questions about what questions do you have or what comments do you have about the things that are happening thus far? About the tech stack, about other stuff? All right, I got a first question over here and then over there. Jesse's going to come with a mic.
Do you expect your scientists to be using the same data frame that you are doing, or are you doing it on their behalf?
Am I doing on?
Their behalf. Like they give you the data sets and then you run it for them, or do they run it themselves?
Yes, good question. So I think ultimately the role of a data scientist is to produce something that looks like software but is really powered by high-powered machine learning and statistics. So the initial wave of work that is me figuring out what I need to do, what needs to be shipped to them, they're giving me sample data. But ultimately, when we deploy this on our compute platform or on like Modal on the web or something like that, it's a command line tool that runs in the cloud. I want them to just submit a file on their own, or even better, I want there to be automation such that the data processing by in this case, statistical model, a Bayesian statistical model, is actually done on the cloud automatically with no intervention by humans. One more question over there.
Yeah, I just have a question around how you do sort of tracking of things like data provenance. I think you're pulling in the JSON file is a great example.
Yep.
It happens all the time.
Yep.
I've got this data, let me just pull it in, and I can just have the agent do that.
Yep.
But you want this to be fully reproducible, I assume.
Yep.
So do you have best practices or guidance around how to do that, capture these sort of one-off things that you ask the agent to do, but if you want to recreate all of that, is there a good framework for doing that?
Yes, ask the agent to actually record what it's doing inside the notebook. Because the notebook is the canvas. It is the conversation canvas. So first, there are a few angles to answer that, by the way. The first one is if I'm telling the agent to do something kind of ad hoc on the fly, it needs to record it inside the notebook. In my agents.md is a comment that says, you have to add in markdown explanation about everything you're doing. So that's happening over here. That's the first piece. Second piece is this. For data provenance, so I'm not talking about the ad hoc pulling in of temperature that we just did, but actually, where did the files actually come from? That is a turtles all the way down problem, right? You can keep tracking all the way up to finally the raw machine. And ideally, actually, you do want to have provenance of every single transformation that was occurring. And so having systems of record, systems that produce data that go in, systems that produce operational information that go into systems of record, that's very important. That is to say, like at Moderna, if we have our compute tasks running, they produce logs. Those logs go into a system of record that then allow me to trace back this file came from that compute job, which has these logs, which then was pulled from this S3 bucket, which then is known to be the canonical data source, that data dumping location from the machine, right? Like that level of data provenance is required. And then if we have version control on the output data, conditioned on version control of the source code that does the Bayesian estimation, then we need to enable that as well. And that is a complex problem. It's a software problem at the end of the day. Okay. Something happened. So let's just see here. So they're also in the Parquet file. It looks like it's missing, and it may be because head only shows a few columns. That might be it. Okay, so I was missing that. Let's just see here. Explore. Because we have 15 minutes, I'm gonna trust what the agent says. You shouldn't, okay? I'm gonna trust what the agent says and just say, okay, cool stuff. We're gonna home in on on yeast, because we all like drinking yeast products, right? So we're gonna home in on yeast and do only yeast meltome. I want you to isolate out for me everything that came from Saccharomyces cerevisiae lysates, and then find for me one of the curves, one of the data set, find for me data set that comes from one of the proteins that has a very good dynamic range between the upper bound signal and the lower bound signal, because that is a prerequisite that you need to plot a melting curve. If the thing doesn't melt over temperature or is very labile and melts straight away, that's not something that I want to be able to start with when I'm building a Bayesian estimation model for the melting point. Okay, more questions? Up front, Jesse, let's do. Yes.
So a lot of agent these days, the token costs are increasing over time. So can you tell us a little more about, have you run into this question, issues of cost, or what kind of foundation models are you going to use?
The answer is Chinese open source model. Sorry, I'm just joking. If you happen to be in a position, in a privileged position where you have unlimited token streams for zero marginal cost, please take advantage of it while it lasts. All right? If not, the answer still is Chinese open weight models. and this one I actually mean. If you'll notice, I'm using Composer 2.5. It is by the Cursor team. It's actually a post-trained Kimi-K 2.5 model that is hosted in the USA. Personally, on other systems, when I'm at home, I use GLM 5.1 hosted in Singapore. The key thing that you need to be worried about, and these, by the way, are very, about like approximately 10 times cheaper than the latest Opus or OpenAI Codex models. One of the things and they are good enough, more than good enough for coding tasks like these. All right, cool. And so if you can get access to some of these, say via the Olama Cloud, which hosts GLM, Minimax, Kimi K2, et cetera, or if you want to go directly through cursor or something. Those are all viable options. But I'll also note, anything that I'm showing over here is doable by a Sonnet class model. So you actually don't need to use Opus or higher. You can use Sonnet class models, which is roughly, I think, equivalent to GPT 5.1 if you're in the OpenAI world, or Gemini 3, the cheaper Gemini 3 models, which will work perfectly fine as well. There is a world in which now I think we need to start thinking, yes, we need to start thinking about the cost, but not as hard as you might think, because a lot of options are out there. Okay, so we have one of those things plotted out here. We have a little bit of a good dynamic range. Okay, cool. I would like you to now use PyMC to create a 4-parameter logistic curve for P32844_SEC6. We'll just do it for this one protein first and try to see whether we can estimate the melting temperature with uncertainty of this particular protein. You should note that the upper and lower bound, the absolute upper and lower bounds really should be 1.0 and 0.0. So there shouldn't be any ambiguity about this one, unlike in other experiments, for example, where the upper and lower bound value might not be well defined. So let's go ahead and use PyMC to fit this curve. And what I want at the end is a plot of what the estimated melting temperature was versus what the authors originally estimated as the melting temperature versus our estimate with uncertainty. So I'd like you to plot a posterior plot which will show the distribution of our posterior estimate of the melting point with the reference point being the actual data. And I want you to use RVs to do this with matplotlib. Okay, it's going to cook some more. Any more questions? Up front. Okay, I'll repeat the question.
I couldn't frame this as a question, but I just wanted to point out that using Marimo is great because, unlike Jupyter, everything is reactive.
Yes. Thank you. So you know it.
The state of the notebook is always reactive. We can never will have output itself.
Yes, exactly. And so actually, so the comment is that Marimo notebooks are fully reactive, which means unlike Jupyter notebooks, where you can have a cell that goes out of date, it gets stale, and if you were to trust that output, holy smokes, bad things can happen, like dividing by 0. Okay, so one thing that Marimo solves is a fully reactive notebook means all downstream cells of any cells that are changed are fully recomputed on the fly, and so you'll never get a stale cell ever. And actually, while I was rehearsing and prepping on the microRNA data set, which you all didn't want, it turned out I was loading the wrong data frame right at the top, the wrong CSV file right at the top, and so I was like, okay, buddy, coding agent, you got to change this to use the other CSV file, and it just changed one line, reran all cells below, perfectly recreated everything that I needed. Okay? Next question. The agent is still cooking.
Going back to the model choice and price question, do you run into any situations in your standard workflows like this where you do actually need to step up to like the Opus models or the more advanced models, or do you really find these simple ones that kind of fit all your use cases?
Yeah, so at work, because sometimes we touch lipid nanoparticles and viruses, viral proteins, we get censored by the regular GPT models. And so I've had to switch over to the Roslyn model to make that happen, to enable me to actually do my work. So they call the Roslyn model the life sciences model, but it codes perfectly fine. I'm not trying to design a protein that kills the world or something here. I'm trying to save the world at Moderna. So so sometimes I've had to do that. And there are corners of LLM knowledge that are not, it's part of the ragged frontier. So this one it's not the part that's pointing outwards and really capable. It's the one that's really close to like being dumb, because it's not in the training data set. Like that info is not in the training data. And you can kind of grok it, right? Like it's basically, if something was released after a model was released, it's guaranteed not in the training data. And in fact, because of how long it takes to train these models, if a piece of information is released after 6 months before the release of a model, so you walk back 6 months and you say that's the time, anything released after this time point is probably not in the model training set. So you should be able to then go and figure out like whether you need to use a more capable model to help figure out these like weird patches. So right now I'm using Composer 2.5, which is roughly Sonnet 4.6 plus-ish, right? And it's handling 4-parameter logistics perfectly fine because this is so routine. But if I were to do what one of my friends, Sebastian Walcotter, is doing, which is to create your own LLM inference engine, holy smokes, he's had to use Opus 4.7, 4.6 all the way, right? Like he cannot use the cheaper models for this kind of task. Okay, so we have the 4PL curve made. Again, because I have 6 minutes left, I'm not going to check the code. You should check the code if you're doing this. The PyMC model, I'm just going to quickly glance at it and just see whether we have it here. It's right here. And I'm going to only half quickly check that it looks OK. It did the right thing. It's doing 1,000, 1,000. I like that. Target accept 95, 42. Of course, it put 42 over there. And let's take a look at the posterior melting temperature. Hey, look at that. Did that perfectly fine. All right, we got 5 minutes, 45 seconds left. Let's try one more thing. OK, expand this out now to a hierarchical Bayesian model where the melting temperature is where we want to, melting temperature estimates is where we want to have a population prior over the melting temperature. We do not have to have population priors anywhere else because 1.0 and 0.0 are still the thing that we need, and the slope is like whatever as well. So we're going to start with this simple model first, and then I want you to then plot me a forest plot of the yeast proteins, rank ordered by the probability of superiority of the melting temperature. So I want to find the really thermostable proteins. And then I also, separately, also want to have a diagnostic for that is based on the posterior curves for anything that has really high uncertainty, because that probably meant that these things didn't melt, or they were already melted right from the beginning. And so we get a crap curve, and we have very high uncertainty. So go make this for me. OK, agent's still cooking. What else would you like to ask or discuss?
You have to press the button.
Oh, I need to press the button. Thank you. You were all waiting for that, right? All right. Any other thoughts, questions? In the back. Way in the back.
Hi, so we all chuckled when you said the slope is like whatever as well, but I am curious, each time you're speaking to an AI tool, how do you make sure you give it all the information it needs and, I personally was concerned with AI that, if I give it one wrong thing, something goes off in a totally wrong direction. So how, when you're giving it this prompt, just spur of the moment like that, not even double checking it, how do you know that it has everything it needs?
Very, very good question, because this morning as I was rehearsing the microRNA one, I went off the loops as well and had to spend a whole talk's time worth getting back into action. So a lot of clarity of thought is really important. So I'm walking in knowing exactly what I want. If I were actually in a situation where I didn't have a clear idea of what I wanted, the key idea with agentic data science now is to slow yourself down and ask for only one small thing. Of course, I'm in a demo, so I'm really pushing hard here. But if I were doing this, I've done 3-hour pair coding sessions with a coding agent where parts of the analysis I was like, no, hey buddy, I gotta slow down, right? I need to produce one plot that tells me the diagnostic, and I'll spend 5 minutes thinking about the plot. I'll go get some kombucha, go walk around for a little bit, come back to my computer and go, okay, I know exactly what I want for this one little plot. Make that plot, show me. Then make it interactive, right? Add a little drop down that lets me flip through the samples and look through the samples one by one just to sanity check my understanding. So it's really important to know when you can be fast and when you need to pull back and slow down. You can be fast when you're operating in your vibe zone equaling your zone of expertise. So I've done Bayesian 4PL models before. I'm going fast. If you ask me to do analytical chemistry, I'm slowing way down because I've never been trained properly in analytical chemistry. So I'm going really, really slow, making sure that I do things one step at a time, logical step at a time. And next one.
I was wondering if you ever ask the agent to do something parallel explicitly, and how do you decide
When to go parallel and when to go sequential.
Yeah.
Yeah, I will counsel as much as possible go sequential, because the explorations that you do, you want to sequence it through an order of priority of importance of what you need to do to get your job done. You can have a lot of parallel explorations coming later, and parallel explorations are great in the regime where you have a thing that you need to very quickly optimize, or you need to very quickly go through lots of exactly the same options. So you go sequential to build up what it looks like for one exemplar, and then parallelize afterwards. But for the most part, it's going to be sequential. That's been my experience. Okay, let's see what's happening. Oh my gosh, it's fitting. Yes. And it's actually within time. We have a minute left. We actually have 55 seconds left. I'm seeing the clock here. Let's see what it does. I hope it finishes. If it doesn't,
No more questions, right?
there's probably no more. There's probably not enough time for questions. The coding agent through the Marimo pair system actually has visibility into the kernel. Oh gosh, yeah. It has visibility into the Python kernel, so it knows exactly what's going on. And so it will go and fix itself in a loop, right? And so there we go. Look at that. If the numbers are correct post me checking, then this is what I would trust. Of course, I have to check it. So with 10 seconds left on the clock, I'll leave everybody with, this is a taste of the future of agentic data science. Thank you.